It's one thing to talk about legendary aircraft, but it's another thing to talk about the SR-71 Blackbird. This thing was, well, it was something else entirely. For decades, it was a machine that flew right on the razor's edge of what we thought was physically possible. So how did they do it? Let's dive into the absolutely wild engineering that made this legend real.
Okay, let's start with the basics, which are anything but basic. The Blackbird cruised at Mach 3.2. That's not a top speed it hits for a few seconds, that's its cruising speed. We're talking more than 3 times the speed of sound, fast enough to zip across the entire United States in just over an hour.
And it wasn't just fast, it was high. It operated at 26 kilometers. That's about 85,000 feet up. Up there, the sky isn't blue anymore. It's just black. You can literally see the gentle curve of the Earth. This wasn't just flying, this was bordering on spaceflight. Now, when you combine that speed and that altitude, you get a plane that was practically invincible. I mean, think about this. If it ever detected a surface-to-air missile launch, the standard procedure wasn't to dodge or deploy countermeasures. Nope, the pilots would just speed up. They would literally outrun the missile.
So, you have to ask, right? How on earth was this even possible, especially back then, in an age of slide rules and analog computers? Well, the answer starts with the heart of the beast, one of the most incredible propulsion systems ever built.
The whole plane was really just designed around its 2 massive engines. And these weren't your typical jet engines. They were this bizarre, brilliant hybrid, basically 2 different engines crammed into one, designed to solve a problem that seemed impossible at the time.
See, here's the puzzle. You've got 2 main types of jet engines. A turbojet, like on an airliner, uses spinning turbines to suck in and compress air. It works great from a dead stop, but it hits a wall at high speeds. Then you have a ramjet. It has no moving parts. It just uses its own incredible forward speed to ram air inside. It's useless at low speed, but it's a monster at hypersonic speeds. The Blackbird needed the best of both worlds.
And the key to the ramjet is this thing called ram pressure. It's a beautifully simple idea. You just go so fast that the air piles up at the front of the engine and compresses itself. No moving parts needed. It's pure physics, but it only kicks in when you're already moving at mind-boggling speeds.
So what did the engineers at Lockheed do? They built an engine that literally transformed in midair. The Pratt & Whitney J58 started as a turbojet to get the plane off the ground and up to speed. But then, as it got faster, a series of ducts and bypasses would open up, rerouting the air around the main turbine and directly into the afterburner. The whole thing basically turned itself into a ramjet while flying. It's just wild.
Okay, but that creates another huge problem. You can't just shovel supersonic air into a jet engine. It would be like trying to drink from a fire hose. It would completely destroy the delicate machinery inside. You have to slow that air down, which means you have to somehow control a violent supersonic shockwave right at the engine's entrance.
The solution was this giant movable spike you see at the front of the engine. As the plane sped past Mach 1.6, this spike would physically move backwards, up to 26 inches, to keep that shockwave perfectly positioned. At the same time, a whole system of bypass doors was constantly opening and closing to manage the pressure. It was this incredible mechanical ballet, all happening automatically at thousands of miles an hour. And if any part of that ballet failed for even a split second, you'd get something called an unstart. The shockwave would get violently spit out the front of the inlet, and one engine would instantly lose almost all its thrust. The plane would then yaw so hard to one side that pilots said it was like riding a bull. It was a constant, terrifying risk they had to live with on every single flight.
Now what's really crazy is that these engines probably could have pushed the plane even faster, maybe the Mach 4 or even Mach 5. So why was the official speed limit only Mach 3.2? Well, the problem wasn't the engines. The problem was the plane itself.
And that brings us to one of the most famous quirks of the Blackbird. It's about the fuel. You see, the fuel wasn't just for propulsion. It was actually part of the plane's structure and its cooling system. It was a leaky, brilliant, and totally bizarre solution.
First off, just look at this. The SR-71 was, for all intents and purposes, a flying fuel tank. Almost 60% of its entire weight on takeoff was just fuel for those ridiculously thirsty engines. We're talking about an enormous amount.
And to save every possible ounce, the engineers got rid of separate fuel tanks. Instead, they just pumped the fuel directly into sections of the wings and fuselage. The skin of the airplane was the fuel tank. This is known as a wet wing design, and it led to a very interesting problem. Because of this design, the Blackbird leaked a lot.
On the ground, it would literally sit in a puddle of its own jet fuel, and this was on purpose. The titanium panels of the skin were built to fit loosely on the ground, because they knew at Mach 3, the airframe would heat up and expand by several inches, sealing all the gaps. They actually had a checklist for an allowable fuel leak rate before it could take off.
But the fuel's cleverest trick was its second job. This special JP7 fuel was incredibly stable. You could throw a lit match into a bucket of it and it wouldn't ignite. Because it was so stable, they used it as the plane's coolant. They pumped it all through the airframe to absorb the blistering heat before it ever even reached the engines to be burned. The fuel was literally cooling the plane that it was about to power.
And that right there, that's the real answer. The thing that ultimately limited the Blackbird wasn't its engines or how much fuel it could carry, it was heat. Pure, simple, and absolutely brutal heat from air friction.
Just look at these numbers. At Mach 3.2, the nose cone would reach over 300 degrees Celsius. The area around the engine could hit nearly 650 degrees. That's hotter than your oven on its highest setting. Regular aluminum, what most planes are made of, would just turn to mush at those temperatures.
So the engineers fought back with a three-pronged attack. First, they built 93% of the plane out of a special titanium alloy that could handle the heat. Second, as we just saw, they used the fuel itself as a giant circulating coolant system. And third, the paint, the very thing that gave the Blackbird its name.
Which, if you think about it, seems completely backwards, right? We paint passenger jets white to reflect sunlight and stay cool. So why on earth would you paint a plane with a massive overheating problem black, the color that absorbs the most heat?
Well, the answer comes from a cool piece of physics called Kirchhoff's rule. It basically says that anything that's good at absorbing heat is also really good at emitting it. At 85,000 feet, the heat coming from air friction was way more of a problem than the heat coming from the sun. So that special black paint was designed to be an incredibly efficient radiator, just constantly beaming all that dangerous friction heat away from the plane and out into the cold of space.
The SR-71 flew its last mission years ago, but the lessons learned from it are still pushing aerospace forward. Its spiritual successor, the planned SR-72, is aiming for Mach 6. It's expected to be an autonomous drone built with advanced composite materials designed to handle even more extreme temperatures. You know, the SR-71 broke the barriers of its day. Titanium, hybrid engines, thermal management. So as we look ahead to a future of Mach 6 flight and beyond, it just makes you wonder, what new, seemingly impossible engineering limits are the next generation of pioneers about to shatter?